Hi, this is Matt, and this is going to be a follow-up video on my first one about my conversion of a old drill press to a homemade mill. I've since done quite a number of upgrades to this. I've used it quite a bit with pretty good results. And I noticed there was some interest in this type of project, so I'm going to follow up and maybe go into a few details that I missed in the first video. So just a quick view of the whole unit here. This is an old, I believe it's a Porter cable drill press. Not that old. I bought it at, I don't know, maybe 15 years ago, and it served me well for what it originally was, but I wanted a mill with more capability. Since I'm getting into some machine work, I've also bought a lathe before I started this project. It was actually a pretty nice lathe. I've been very happy with this. It's a Precision Matthews BV 1440. And it's a Asian-made lathe, but it's one of the higher grade ones. Precision Matthews does a great job on getting these custom spec'd out the way that they want, and I've been very happy with this machine. Very powerful machine. Anyways, back to the mill. So one of the things that I've done here to start is I've since taken off the old 3/4 horsepower single phase motor that came with it, and I've replaced this with a 2 horsepower. A little bit of overkill. I probably could have done with just one, but I wanted to be sure that I had enough to do what I wanted to do. And I've had no problems with this at all. It runs beautifully. This is a 3-phase, 2 horsepower motor. Now I don't have 3-phase in the shop, but it's not needed anymore to have 3-phase to run a 3-phase motor. Some people used to do an old trick where they put 2 of them together, and one just idles and it generates the other 2 phase from a single phase. The thing is, they still only run at 1 speed, just like in a regular AC 110 motor. But now they've got VFD drives like this up here. And this enables you to do all sorts of things that you couldn't do before. The big thing is that it allows you to run it at multiple speeds, and it's quite a range. This goes down to less than 1/10 of normal running RPM, all the way up to about twice the original running RPM for the motor. So that's been one upgrade. I had to do a little custom mount here. I had to add a plate because it is a bigger frame size than the original, but I do welding, so it's not a big deal to do that. It's the same original belt setup in here. I'll show a little more of that later. We got some electronics up here, but I'll go into that later. The other thing I've done is I have added a DRO system to this, and it did this in 2 stages. First, I just did X and Y, the table movements. So we got down here, if we can see. I've mounted an aluminum bar onto the actual base setup. Well, there's one down on the base for the reed head down here, and this one is on the moving part of the Y. So that moves with the table and the Y motion. I don't know if we can see that in the video. Yeah, okay, that shows. So, and you get a differential in here, and that reed head picks it up. These are glass scales. And then on the Y, basically the same thing. You mount an aluminum bar onto the table itself. And the reed head, well, it's covered over here with the protective covers, but underneath there is another reed head that's just the same as the one that's up under here, which you can just barely see poking out. And that would be mounted to the moving part of the y-axis, which is also the stationary for the x-axis. So you'll see that reed head down in here. If we can get a little light in here, you know, it's kind of way down there, but you can see that you've got the lips down here where the reed head pokes up through. And you can see the wire going down there. Way down there is the reed head itself. It'd be that little box just underneath of here. So that part stays stationary with regard to this part, and this will move in and out as I move the x-axis of the table. I also wanted to follow up on this. I didn't mention in the first video, but this was here, the table itself. This is an Indian-made table, and it's fairly inexpensive. I really feel like these are a great deal for somebody doing a light project like this. It's a very heavy made table. It's a nice heavy piece of cast iron. Thing weighs, I think it's a little over 40 pounds. And it's got great stability to it. You know, you just have to adjust your gids on here, and it's got nice adjustments for them, for both X and Y. It's got these little finger nuts on here, the wing nuts. These are to lock your positions. If you want the table to be stationary for a certain operation on one axis or the other, you just tighten these wing nuts up, and it'll lock the position in. You're going to get these on eBay really cheap. They're like about 140, 150 bucks, which to me, it just seems like a great deal for what it is. I mean, they're not perfect. They've got some flaws. One of the things is the movement on the table, particularly on the x-axis. It's kind of lopsided. It goes way out going that way, but still not as much as you would expect. The handle starts to hit down here. And it'll go about a quarter. And actually, I've already modified this to get more range on it. And coming back, this edge of the table only goes up to right about there. So when you go the other way, this way it extends out pretty nicely. But let me see if I can get it back here. Just take a minute. And it doesn't have a stop on it, so you got to be careful not to run too far. I don't know if you can see it here. I put a little mark right there that tells me that's where I'm going to run out of thread. So that's a good idea to do with these tables. Just so you don't run to the end and have to futz around with trying to get it rethreaded back on. So yeah, this is the other direction it goes. You know, it's not really centered properly on here. Actually, I got it backwards. It runs further off on this side than on the other side. But originally, this was even more to that side, and it wouldn't run in as much. And what I did, the block that the lead screw runs into, I repositioned it inside, and that enabled me to get a little more movement in it. Along with that, if we can see it in here, let's see, if I can get enough of a view, you can just barely see the block up there, and I had to carve out let's see, can we get it this way? I had to carve out a little bit of the casting right on the bottom. Basically, it was a bit of a pain. I had to take the top part of the table off of it, and I set up a mill bit in here and just kind of, because my original table on the drill press can swing side to side. I actually used that to get the motion in there. And I also use the y-axis. So I kind of move it in a little bit and then use the y-axis to move that part, because it was this casting that I was cutting, so I was able to do that. And I re-ground a new spot for the block, and then also cut out some clearance. And what that clearance was for is down here where the end of the lead screw is, and you've got the bearings up in here and the end of the table. So some little things you got to do to make this table a nicer table, but for what it cost, if you put a little work into it, it really is a nice table. I've done quite a bit with this. It's tight, it's solid, and I'm pretty happy with it. The worst problem I had with it is the shipping from India. It was just kind of thrown in a wood crate, and this particular one kind of had a rough ride. When I got it, the handles aren't mounted on them. They leave them separate in the box, but the lead screws still come out, and they apparently got whacked pretty hard on the end. And there's a very slight bend to the x-axis screw on there. It's not enough to disable it, but I do feel it. Out here it runs pretty smoothly, but when you get all the way in and you're up where things start to get tight, you start to feel that little bit of wobble in there. The handle kind of goes loose and tight as you go around. But hey, for $150, I can still get accuracy down to at least 0.1 millimeter that I can get out of this according to the DRO. So I'm happy with it. I also should quickly add in about this Indian table. One little inconvenience I forgot to mention. On the T-slots here, originally these were just rough cast. They worked with their own bolts that they had that came with it. It wasn't anything standardized. So the other thing I did is I milled out. I bought a T-slot cutter. This is a standard size for smaller mills. And I cut out the T-slots down to a standard nice square fit that work with regular tie-down tools. It was a bit of a pain because I don't have another mill, and I really didn't want to pay someone to do this, but I managed because, like as I mentioned, the original table on this will swivel side to side. So I did it in sections and just milled on the table itself using the table itself. It's not a perfect cut. I mean, there's a very slight zig in them, but it's not critical because I don't use these for alignment for anything. They're just for tie down. If I do any alignment, I do it off the edges of the table. So we've got our VFD drive is mounted up here with a whole control panel. Got a main power switch, shuts everything off, including the VFD drive. When I'm off for the night, protects from surges, anything like that while I'm gone. This is a little power supply for some of the controls and lighting and a RPM meter. So here I've got my controls mounted. So I've got the basic start, stop. This is our RPM readout. tachometer. And these two buttons I use for threading. And it's a very slow forward feed and a slightly faster reverse. And I use this for threading. I use the manual feed control, the fast one, and I'll just put a steady pressure on and run the forward, and this goes really slow, and it's got a slow acceleration too. So when I let go, it stops almost instantly. So I'll go about 2 to 4 turns, and then I'll let go, and then I'll back up just a quarter turn or so, and then go forward again for threading. Of course, this isn't a threading bit that's in here, and if I'm running a bigger bit, I can actually make that go slower by turning my belts down. So the actual running speed, right now I've got it set on high with a medium belt speed. So just accelerate up. Got about 3,400 here. I've got to control this. Is hooked up to the VFD, so I can turn it down. Got quite a range on it. Tachometer I've got hooked up in here. Made a mount here, I've got a pickup, and then the meter's up there. And that little white cap has got a little magnet inside it. In fact, you can see the pulsing here if I slow this down. Get it slow enough that the camera can pick it up. So you see that flashes every time it picks up the back and going around. It feeds into the tachometer. So right now this is an intermediate belt speed. If I put this on the high belt speed, it'll go as high as about, I forget the exact figure, but it's over 6,000. So one of the other things I've done here is I've hooked up the Z-axis on my DRO. And this took a bit to figure out how to do this, but I finally got it. So let's see it a little better here. So I used the original stop bracket down here, and I changed this. This used to just be a manual stop. That piece is original. It's got the little button on it where you can set the height, and originally it had a scale on here. One side was flatted, but the length wasn't that tall. It just went enough to cover the depth of the quill. But I needed a little more to mount the hardware on here, so I replaced this with a 1/2 inch fine thread, which was what it was originally threaded at, and cut it to length now so that I can get everything bolted on here and cap up my hardware to mount the DRO scale. And this is just welded out of some angle steel, and well, it's actually, this is a hardened angle steel. From a framework, and some framework steel that I cut to make the brackets here. I did this in CAD work, made a plastic template, and then copied it out. And then I've got a bracket. I don't know if we can see this from back here, but there's a bracket mounted to the cast iron of the press itself for the stationary portion. So if you watch this in motion, just as I lower the quill. No, I don't have a lot of room here, but let's see. There we go. So the glass scale portion goes up and down with the quill, and the reed head stays stationary and is mounted to the cast iron of the press itself. So let's see if we can see this here. I lower it, Can we get both in the shot here? So you can see the readout as that scale goes down. I showed where I did the threaded rod here, but I forgot to mention the Z wheel here. You've got your fast motion here, but on this side here, what I've done is I've got a little finger wheel that lets me turn this manually in very fine increments. So we just turn it like this. Now I did this is just printed in nylon right now. I am going to do this in a piece of steel later. This is just the first draft to test it out and get me up and running. It actually works quite well, except that it really wants to stick to that threaded rod so it doesn't spin that freely. You have to put a little force on it. When I do this with steel, I should be able to just tap this and let it spin up pretty freely. And there'll be a nylon washer top and bottom, which I'll probably reuse these ones that are here. And lastly, because the steel will spin a little freer, I don't want vibration turning it when I'm doing a cut. So I'll drill a hole in here and do a little thumb wheel. And if you can see in here, there's a little groove in that plastic, which the thumb wheel will go into that groove. The reason for the groove is because if I just do it flat and this is a tight fit in the journal, putting the set screw on there is going to mar the surface and eventually it'll cause binding in the journal. So I do a slight insert and the screw goes on that so the marring won't interfere in the journal. It'll be inset from it, and the bearing surfaces will be top and bottom. So I'll have a nice top fit and help prevent jiggle down here. So that pretty much completes that, and that'll wrap this up for now. Oh, the templates. I mentioned the templates for these brackets. What I did for that, little tip if you want to do some work and you don't have CNC on your mill, which I don't here. I have a 3D printer, so I did my CAD work and I just made these little templates. They're about 2 millimeters thick and cut exactly to the dimensions that I want. And first I cut these out with a plasma torch, just a rough cut, a little bigger, and then I take this on the mill and just sandwich it with the piece that I cut. And I'll just mill right around the edge till I just barely touch that plastic and I come right around it, and then I've got a near exact copy of it that's good enough for the work that I'm doing.